Hello, everyone. Good afternoon or good evening. Thank you all for being here today in our event. I'm Professor Reginaldo. I'm a professor at the Universidade Federal Fluminense and a member of this organizing committee. Let's begin one more section. And I'm pleased to introduce our first speakers of today, Professor Edgard Pimentel, from Pontifical Catholic University of Rio de Janeiro. He is a specialist in regularity theory of nonlinear partial differential equation. Today, he will talk about non-convex Hamilton-Jacobi equations with gradient constraints. Professor Edgar, thank you for accepting our invitation. Please, you can proceed now.
Thank you, Reginaldo, for this very nice introduction. I'm very happy to be here with our friends from Universidade Federal Fluminense. I want to thank you very much for this invitation, and it's a joy actually and an honor to be here, because in fact in this difficult times this is a very nice opportunity to see our friends, to greet our friends, and to make and somehow to give some energy to the community. So I want to thank Juan, Carlos, and Reginaldo, and Ms. Viana for this very nice invitation and for this very nice opportunity in this workshop. It's an amazing program, and I'm not sure why you guys believe I'm suitable to be here. The program is very nice, and I'm very happy. So let me start talking about this thing. So today we're talking about non-convex Hamilton-Jacobi equations with gradient constraints, and the most important part of my talk is this. This is joint work with this friend Hector Andres Changlara from CIMAT in Guanajuato. I first met Hector in Stockholm in August 2019, if I'm not mistaken, and I believe I'm not. And then in December 2019, I went to Mexico to visit Hector, and then we start working in this project. And I mean, Hector is a very nice individual, very nice friend, but he's also a very nice mathematician. So it was an intense period for me. I was learning new things, and there was this funny fact. In the morning, we would meet, and then he would say a lot of things that I had never heard about, and then I would have to study by myself for a couple of hours to catch up. And this is to say, I learned a lot with this very fine individual that you're seeing on your screen, and with this also very nice view of Guanajuato and central Mexico. So this is the important part of the talk. Now let's move on to the outline and just to check what we're talking about today. So the first thing is, well, we are dealing with Hamilton-Jacobi equations, and our equations here, they impose a constraint of the gradient, right? So we have a constraint on the gradient of the solutions, right? And they are formulated in the non-convex setting. So one of the features in the non-convex setting is the fact that the gradient starts out as an unbounded quantity, right? And this is something that plays a role in what we are doing here. Well, this plays a role in what we are doing, and it relates to important things in the literature. So there is this saying that once upon a time, there was a family of equations that used to hold only in the regions where the gradient was large. So somehow the problem we are addressing here touches this class of equations, and we'll talk a little bit about it. And okay, so these two first topics are about the model and what happens and why someone would be interested in studying this class of equations. And then the third thing is what do we do, right? So we try to understand, or we try to tackle the issue of optimal regularity for the solutions, and we understand solutions here as viscosity solutions. And then there is this unusual thing that this optimal regularity and beyond, right? This is pretty much nonsense, because if you have optimal regularity, it's supposed to, you don't have beyond. You don't go beyond optimal regularity. Well, not that fast, right? The thing is, you have optimal regularity, but you might be lucky enough to be able to improve somehow regularity of the solutions along certain structures, or in our concrete case, you might come up with a structure or a quantity depending on the solutions, and then improved regularity applies to this thing, right? And the last thing I want to share with you is just a comment. There's perhaps a very silly one, but it's about recent thoughts that I had. There is the connection between viscosity solutions and the strong solutions, and how these things would connect in the context of this problem, right? So let me start with the model. And this afternoon we study, or this morning or this evening, depending where you are in S3. So what we are studying today is this PDE. So this PDE is just a way of putting together two very simple equations. So we start with the Poisson equation minus Laplacian of u equals to 1, and the iconal equation gradient of u in norm equal to 1, right? And then you say, well, we have these two very nice equations, they are together, we don't know what to do, let's take the minimum, right? So this is the problem we are studying today. So here for us, omega is a subset of our D, the D-dimensional Euclidean space, and we suppose this set satisfies a uniform exterior cone condition. This is just something on the geometry of the, how's it called, of the boundary of the domain, right? If you don't want to think about stereo cone conditions, you can think about stereo sphere conditions, or if you don't want to think about conditions whatsoever, you just can replace omega with B1, right? And don't care about it. So we work under the notion of viscosity solutions to this problem. The notion of viscosity solution as introduced at the beginning of the 80s in the work of Crandall and Jones, and Crandall, Evans, and Jones, and the way it developed till recently. And one thing is, if you pay close attention to this problem, you notice, well, this is degenerate elliptic in the sense that it preserves order, or in fact reverses order, since we have minus the Laplacian when you take into account symmetric matrices. But this is not uniformly elliptic. I mean, in the sense that if you are in a region where minus Laplace of u minus 1 is above the gradient minus 1, then the PDE is a first order PDE, and you don't have a second order gradient, right? Okay, so you see, there is a funny thing here, because the gradient is bounded from below, right? I mean, the minimum of these two quantities is 0. So if the minimum of these two quantities is 0, what it means is that both quantities are greater than or equal to 0. So what happens is this. You see, your gradient in norm is larger than or equal to 1 in omega, right? So, well, this is not a nice way to start things, right? Because it would be a very nice fact if we start out with a gradient that is bounded. I mean, couldn't be bounded by 1, could be 19 or 1983, a very, very nice number. Could be whatever number you choose. But if you have the norm bounded from above, then this is a good thing. You start wanting to become Lipschitz. But if you're bounded from below, then this thing can go crazy and be whatever it wants. So these are some of the features in this problem, in this model, and they somehow guide our intuition through the technicalities and the classes of results we prove. So let me continue with an interesting perspective. And it was something that when Hector shared this perspective with me, I was pretty much amazed. I mean, this is a very interesting way of thinking about this problem. So there is a game theoretical approach to this equation. There is more or less like this. You see, you start with a particle in a domain omega. Your domain satisfies wherever you want, or is just the unit bulk. And then what happens is that this particle moves along inside the domain until it reaches the boundary, right? When it reaches the boundary, it gets a check or a suitcase full of money and go home, right? And then what happens is this: you have two players. And the choices of those players is what determines the dynamics of the particle x0 and these choices are taken every and each time interval dt, right? So how things work. So the first player wants to maximize the time, the amount of time that x0 stays inside the domain. On the other hand, player 2 aims at minimizing this amount of time. So you have a particle running and moving inside the domain. And what happens is one of the players wants to last as long as possible, whereas the other one wants the game to terminate as soon as possible, right? And how they make choices? Well, you start the world at time t, and at the beginning of the interval t plus dt, player 1 makes a choice. So her choice is either to say Brownian or aconal. What does it mean? Well, if player 1 chooses Brownian, the particle x0 moves according to a Brownian motion, a standard Brownian motion inside the domain. However, if player 1 chooses iconal, it means the particle will move with constant speed 1, but in this case, player 2 chooses a direction, right? And then after as this time interval ends, the game is played once again. So player 1 chooses the dynamics, says, oh, this is either Brownian or iconal. And in case player 1 chooses iconal, player 2 is called to action, is called to make a choice, and her choice will be just a direction in S1, right? So let's see a picture. This is a domain. This is a very nice domain. And well, what happens? This is omega. Omega satisfies the condition, the exterior cone conditions, and satisfies some other conditions as well. So what happens here is you have this particle x0, right? So if you pay close attention to what's going on here, you see x0 is close to a large amount of boundary, right? There's a lot of boundary in the vicinity of x0. So if player 1 chooses Brownian, the Brownian motion moves very fast, and it's much faster than something with speed 1, right? So what's going on here? You have a lot of boundary in the vicinity of x0. If player 1 chooses Brownian, then there is a higher probability that x0 hits the boundary. Because you see, it moves very fast, and it's a lot of boundary available for this point to touch the boundary. On the other hand, the point x1 is such that in its vicinity, you don't have that much amount of boundary, right? You see, there is a boundary here, there is some, well, so if you choose Brownian, the equiprobability of the Brownian motion may very much get this x1 inside this region, and then this guy starts walking here, and then Brownian kicks in, you see? So why is this picture here? This picture here, first, is just to celebrate the things we have around here in Rio de Janeiro. And the other thing is, you see, if you have a particle located in a convex portion of the domain, very close to a convex portion of the boundary, then it's better to player 1 to choose iconal. On the other hand, if you are close to a convex, and of course, convex or concave depends on the perspective, right? If you're inside or outside the domain. But, and since I'm always confusing convex and concave, I don't want to say where I am. But the thing is, if you're in a convex region, close to a convex region of the boundary, then what happens is that you choose iconal. Player 1 chooses iconal, right? Whereas if you're close to a geometry like this, you don't have a lot of boundary available in the vicinity, then the optimal choice for player 1 is Brownian, right? The solution to the equation minimum minus Laplacian minus 1 and the norm of gradient minus 1 equals 0 is the value function associated with this game, right? So this is an important take on this how's it called, on this model. And this kind of folklore the way to tell the story is a simplified way, but this type of model appears in several applications, mostly in math finance and problems in insurance mathematics and this kind of problems, right? So what are the fundamental questions we are interested in here? So the first thing is we have to understand what happens with the solutions from the viewpoint of PD-like properties. What does it mean? Well, we are interested in comparison principles. We are interested in the existence of solutions. We want to know if uniqueness is available in the case of a particular problem. Is there stability, right? This stability thing is a very funny fact. I mean, stability is usually referred to in the context of uniform convergence, right? If you have local uniform convergence of solutions, then you have stability. One funny thing is that stability is available also under a different notion of convergence of functions. There would be gamma convergence, right? Gamma convergence usually is thought about in terms of functionals, but you can formulate the same thing in terms of functions. And if you formulate gamma convergence in terms of functions, then viscosity solutions are stable under gamma convergence as well. So this is the funny thing. This is the first task one has to overcome, and this is something important in the context of this model. The second part, well, the next challenge is to examine the optimal regularity of the solution, right? What is the best regularity of solutions in general to this class of problem under the assumptions that, well, we don't have that much structures to make assumptions on, but then you just say, well, let's see what we have in terms of interior regularity and boundary regularity and this kind of things, right? And beyond, right? And now let me make another comment on this beyond, right? Let's make a comment on the beyond. And the comment here is this: I mean, you want to come up with regularity for quantities associated with the solutions that make sense for some viewpoint of analysis, right? And the third thing there is important is to study the associated free boundary. You know, you have this situation, you have a PDE that holds in the region where minus Laplace of u minus 1 is the minimum, but as long as you change to the other region, right, you have the iconal equation. So the question is this: how is this interface developed? This interface develops in a way that depends on the solution. So clearly here, the discontinuity of the operator as something depending on the solution introduces a free boundary, and the analysis of this object is pretty much what we should aim at as well. Okay, so let me give you some context on this fact, on these things, and then we move on. So Hamilton-Jacobi equations with gradient constraints were introduced in 1979 by Lawrence Craig Evans. And in this context, Evans studies this equation, right? You have a linear operator that is uniformly elliptic with C2 regular coefficients. So to some extent, this is just Laplacian, right? And you have the gradient, an iconal equation. Both structures relate to functions f and g, which are C2 up to the boundary, right? Or C2 in the interior and then continues up to the boundary. I mean, we are interested in local results. I will not be too picky about this class of things. So what happens here is that, well, under this general formulation of C2 regular coefficients, then there exist solutions. And if you specialize the coefficients to be constant, then the solutions are locally of class U11, which means that locally the Haitian of the solutions not only exists, but is also essentially bounded, right? So this is the key result in this work, right? Right after that, a number of people, Wigner, Ishii, and Koik, Yamada, and more recently Ryan Hind, studied variations of this problem. And well, one important thing, one funny thing here is that you can generalize either using different operators like linear operators, or you can use a more general formulation on the gradient constraint, or you can weaken the assumptions of C2 regular coefficients, constant coefficients, and obtain still C11 log regularity for the solutions. But the question is, you are here looking at the maximum between these two quantities. And you see the maximums are very powerful. It's a very powerful thing, as is the minimum, but the fact that is interesting for us is this. You see, if instead of the minimum, you have the maximum here, then, well, you start out Lipschitz. You see, because the thing is, both quantities between these parentheses, they should be smaller than or equal to 0. So the gradient has to be bounded by 1. So unlike in our case, the gradient is bounded from below. In this setting, you start off with a very important piece of information, right? You have here that solutions are Lipschitz. And the interesting thing is this jump from Lipschitz regularity to the C11, right? That's to say that you start Lipschitz and you prove that gradient will be Lipschitz as well. But this is a difference, right? Here, when you have the maximum, you have a convex setting, right? You are in the convex case, right? And in the convex case, well, you start out Lipschitz. And this is an interesting information, right? Well, this class of problems, I mean, when you talk about Hamilton-Jacobi equation, it's very natural to think about optimal control problem. And Schreiber and Halima-Tessoner studied convex Hamilton-Jacobi equations with gradient constraints in this context, in particular in the context of singular optimal control. What do I mean by singular optimal control? I mean something like this, where this term U, the zero-order term, appears in the Hamiltonian. This is a very vague definition of singular optimal control problems. I don't want to be too specific or rigorous about it. But the thing is, if you have a zero-order term inside the Hamiltonian, then, well, you're probably, or you're in the setting of this singular optimal control things, right? And then, well, what happens in this papers, studying this class of equations, right? Here you still deal with the convex setting, is that regularity of the solutions is established, and in fact, they are of class C2, and also the smoothness of the free boundary. And once you have smoothness of the free boundary, then, well, you can come up with optimal control processes that are obtained as reflected Brownian motions through the free boundary, right? So once you have enough regularity, you can reflect. And this is the structure used here to produce optimal control processes as part of the analysis, right? Oh, there is a third thing. There is a third thing. I don't know what is this. Okay. Good. So there's a third thing I want to share with you. Recently, Hillenberg and Luis Silvestre studied elliptic equations that are supposed to hold only in the regions where the gradient is large, right? So what you have typically, if you are in this setting, is an equation that can be driven by an extremal Pucci operator like this calligraph P. And what you have is that you have P minus of the Haitian minus, let's say, a constant gamma times the gradient, and this is bounded from above by a constant C, and it holds where, well, this equation holds in the domain into the region where the gradient is above something, and my choice here was to use the gradient strictly above 1, right? So if this is the case, these authors, Hillenberg and Luis Silvestre, proved that solutions are in fact Hilder continuous. Right? This is in the spirit of the Krylov-Stepanov theory, and it's a very nice paper. It's a very beautiful paper, and has some sort of a sequel, although the years are not compatible to this fact, by Connor Mooney, in which the unbounded case measurable coefficients is examined, and the same regularity C alpha is produced. So you see what's going on here. You have an equation. There's the minimum of minus the Laplacian minus U and D and the gradient in norm minus 1, right? So what are you dealing here? In the regions where the gradient in norm is strictly above 1, then you have the Poisson equation. So why is this important? I mean, you go to your bookshelf, and off the bookshelf, you have that solutions to our problem are locally Hilbert continuous, right? And you see, this is funny because in the convex setting, what you start with is Lipschitz regularity, right? But if you go to the non-convex set, and I'm trying to convince you the non-convex set is a very difficult setting, then okay, you don't start Lipschitz, but you start C alpha. Well, it's not the same thing, and it's far from being the same thing, but they are similar, right? And I mean, it's just that the models of continuity is different, right? But still, the question is, you don't start Lipschitz, but you start Hilbert continuous. How far can we go, right? Can we go C11 as in the paper by Craig Evans? Can we go C2 as, I mean, we are not starting Lipschitz, we're starting merely Hilbert, right? So what happens is this. So let me show you our results. So let me share with you our first result. So our first result in the optimal regularity is this. If you use a viscosity solution to the Hamilton-Jacobi equation, non-convex with gradient constraints, then what happens is that solutions are locally Lipschitz, right? And the best we can do is locally Lipschitz. In addition to this fact, for every set that is compactly contained in the original domain, we can come up with a constant that is strictly positive, such that the gradient is essentially bounded in omega prime, and this bound depends on the L-infinity norm of u plus 1 calibrated by this constant, right? And the constant depends, as it should, on the dimension, the diameter of the domain, and the distance of the subdomain to the boundary, right? Well, how do we prove something like this? The key to prove something like this is to consider a regularized problem, which is equivalent to an equation depending on epsilon, whose ellipticity depends on epsilon, right? So what is the thing here? We have that u epsilon is C2 for every epsilon and converges uniformly locally to u, the solution we are interested, right? But then you see, we don't have uniform bounds in C2, of course, because ellipticity degenerates, but we have uniform bounds in H1. And in addition to that, we have that this function W, that is just the positive part of this difference, is in H1 and is subharmonic. Once this function is subharmonic, we have this sort of mean properties, the mean value properties, mean value formulas, with the inequality pointing in the right direction. And then we can prove that u epsilon is Lipschitz, and the Lipschitz, the bounds in the Lipschitz regularity will not depend on epsilon, right? Since the solution to the original problem is unique, then we can take the limit epsilon going to 0, and the result follows, right? And the result, well, has a consequence. That is an interesting consequence because we have two interesting facts in the theory. One is the Rademacher theorem, and the other one is the consistency of viscosity solutions. So combining those things, it follows that the measure of the set where the gradient goes strictly below 1 has to be 0, right? And it follows from the fact that you have a Lipschitz regularity for the solutions, and then Rademacher theorem saves the day, right? Well, what about the beyond? Now it's time for us to reach the beyond, right? I just came up with this joke. I'm not sure it's really a joke, but let's think about the beyond, right? And what is the beyond? Beyond optimal regularity, what we managed to prove is that, in fact, not only the gradient is essentially bounded, but its norm is continuous, right? The norm of the gradient, in fact, is continuous. So what happens is that if you have a viscosity solution to this problem, then the norm of the gradient has a continuous representative. And why is something like this important? Well, it produces a free boundary condition. In fact, what we find is that along the free boundary condition, the norm of the gradient has to be 1. And this is a funny fact, right? I don't know if you're familiar with those movies where people travel in time. right? So you are in a given age, and then you travel time. And once you arrive in the new time, it's kind of confusing. People look weird. So what happens is you're in this region. The gray region is where you move icon, right? Once you escape to the Brownian thing, you don't have time to be amazed. You're in a different time, in a different age. Immediately you're under the Brownian rule. Let's say the Brownian kingdom has the Brownian rule, and then you move according to the rule. If everything goes well, the thing is that the direction you escape into the Brownian region along the normal vector, right? This is one of the implications of this free-boundary condition in this context. Okay, so how do we prove? You see, you have the optimal regularity. How do we go to the beyond? How do we prove that the norm of the gradient is in fact continuous? So this is what we do. So we combine two types of things. We combine the improvement of flatness with the diminution of oscillations, right? And those things will play some sort of a competitive role, but they end up cooperating one with the other, right? So let me tell you what is an improvement of flatness result. So for every parameter, for every pair, delta and lambda between 0 and 1, we can come up with constants eta and rho. There are small numbers and will not depend on the parameter epsilon. And then what happens is, if this orange thing is true, then you can find a linear function L that is close in the L infinity norm to U epsilon, and whose gradient is in this interval, right? So now let me come back to the orange part, right? The first orange thing tells you that the measure of the set where the directional derivatives of U epsilon are above 1 plus lambda is large, right? So you are the directional derivatives are above 1 plus lambda most of the time. Then you can come up with an approximating linear function whose gradient is above the gradient, is above 1 plus lambda, but is bounded from 1 by 1 plus the norm of the gradient, right? Everything here has epsilons, but nothing depends on epsilon. What matters will not depend on epsilon, right? So if this first orange information holds true, then we have this improvement of flatness. But well, you can say it might be the case that it's not true, right? So what is the alternative? The alternative is that you have this diminishment of oscillation, right? So once again, you have these parameters, delta and lambda, and there exists a sigma strictly between 0 and 1, and sigma is not depending on epsilon. And what happens is that if the former orange condition fails, which means that this condition holds, which means the directional derivative is below 1 plus epsilon, 1 plus lambda most of the time, then we have this classical inequality. What do I mean by classical inequality? If you go to a book, you can choose your favorite book on elliptic things, and mine is the book by Luis Cafarelli and Xavier Cabré. And if you go there to the chapter on Evans-Krylov theory, I think this is theorem 6.2, 6.4, or something like this. And what you have is precisely this. You have quantities that once you move from the unit ball to the half ball, this quantities shrink by a universal amount, right? And then what happens is that you scale these things instead of 1 to half, you go from R to R over 2, and then you're happy, right? What happens is that you have enough information. So by combining these alternatives with some sort of technicalities, it is possible to prove, in fact, that the gradient that there exists a continuous representative for the norm of the gradient of the solutions, right? And this is more or less how things evolve here, right? Okay, so let me make a few more comments on these things, and this is more or less where I go freestyle, in the sense that I want to talk about the role of strong solutions and in the analysis of this problem. Right? So you see, instead of starting with the continuous function, there is a viscosity solution to the problem. We start with a strong solution to the equation, right? And while we have a strong solution to the equation, what does it mean? Well, it means that this orange equality holds for almost every x in the domain, right? You see what I'm saying? You know, this guy here, the solution mu is a strong solution, right? So the equation is satisfied almost everywhere. So either minus Laplacian of u minus 1 or the gradient of u minus 1, either one is 0 or the other is 0. Right? So the product has to be 0. Well, but if the product is 0, then what you are in front of is one of those equations that some people like to study, where you have a fully nonlinear diffusion process pre-multiplied by a power of the gradient or a function of the gradient, and then this is a diffusion process degenerating as a power of the gradient, let's say, right? And what is the thing? The thing is that you have good regularity properties for this class of problems. In fact, above the optimal Lipschitz regularity we found here, right? So there are certain questions. The first question is it true that if a strong solution if we have a strong solution to this problem, then minus the Laplacian of this object is equal to 1? So this is the first question one should ask. And why would someone asking this question? In a different paper, in the advances in mathematics, Cyril and Louis Silvestre proved this lemma 6, right? And the lemma 6 says that if you have the gradient of the solutions raised to a power times a fully nonlinear operator equals to 0, then a viscosity solution to this thing is also a viscosity solution to f d to u equals to 0. In some sense, you can divide by the degeneracy, the gradient raised to something, you end up with a fully nonlinear homogeneous equation, right? So is it possible to do the same thing here in the context of strong solutions to this problem, right? And if so, what is the optimal regularity for strong solutions? Do we have optimal regularity for strong solutions? Does it make sense to ask a question like this? I mean, if you have strong solutions, viscosity solutions, you know the optimal regularity for viscosity solutions, what can you say about strong ones? And finally, what are the consequences to the analysis of the free boundary? Right, you see, your Lipschitz. In our case, we are Lipschitz, right? So viscosity solutions are Lipschitz, and this is optimal. Were viscosity solutions C1 whatever, C1 epsilon over 100, I don't care, right? The fact that you have the norm of the gradient equals to 1 along the free boundary would, like a pre-calculus course, you can use the implicit function theorem for C1 alpha functions, and you would have a C1 alpha regularity theorem for the free boundary, right? So it's as if you were almost there, but then you don't get it. And I mean, if we can do better in terms of strong solutions, then perhaps we can jump to conclusions on the free boundary just like this, and more or less for free, right? And with that said, I want just to you see, with that said, I then want to thank you very much for your attention. I think my time is up, and thank you very much for being here.